think the only thing that is left is to introduce Daniel Tolhurst, to whose work there were already quite a number of references in the former session. And so he's working on mixed models and the integration of, well, you see there already on the slide, so I don't have to pronounce it again. Well, Daniel is one of these promising scientists that can integrate, let's say, not physiology, but a lot of statistics with biology. So, the floor is yours.
Thank you very much, Fred. I should probably say that I'll be mostly focusing on the disentangling part today rather than the integration. But nonetheless, we'll see how it goes. And actually, just hearing your talk this morning, I did add up this. It's new, but sort of also old stuff, but reworking of old stuff and how we can rethink that into today's framework. I'm actually just also going to start up and be a little bit cheeky and advertise one of our own conferences next year, late September 2025 in sunny Scotland. We'll be hosting the next UCARPI biometrics meeting with Professor Gregor Goyance, and Hans-Peter Pifo has been pushing away as well. We've also got a Field SimR and Alpha SimR workshop before that. I always like to start my talks with acknowledgements because I think that nothing afterwards really comes without collaborators. So firstly, I'd like to thank PhD studentship that originally sort of set the groundwork for some of the work I'm talking about today, and my supervisors there. But what I'm currently doing is an innovation fellowship that's been funded by Edinburgh, and that's now all done for my plugs. So let's get into some of what I'm going to be talking about today. I'm going to be briefly touching on random regression models. Hans-Peter Pifo gave an excellent summary this just before the break. Fred did an average job before that. He said he'll give me the 5-minute warning. I think I'm getting it now. Sorry. I'm going to talk. I think what I really want to do in this talk is actually not be too married to a particular model, but rather how can we use the models that we've got? How can we use the models that are coming and start to think about disentangling non-crossover and crossover interaction, because these terms have been thrown around a fair bit. And what I really want to do here is actually formalize that a little bit and show some applications and finish up, hopefully. So I guess, again, I don't really need to introduce G/E. We're at the right forum for it, but I'm just going to focus on the picture on the right-hand side there. This is the same spot a year apart in Armidale. And we can see that we've gone from a completely drought year in 2019 to quite a nice luscious year there. And that's actually on a sheep farm. So, I mean, if that's what sheep have got to deal with, I don't know, that's why the plants are really struggling there. And really what I'm trying to do is leverage G/E. And there was a picture put up by Martin before the break, and it had climate change, and it was decreasing our yield. We've got agronomy and breeding going up. And the way that we can think about G/E is it could be a force that puts that pressure down and decreases our rates of genetic gain, or we can turn it on its head, leverage it, and start actually, well, not actually, I mean, we've been doing it already, but continue to improve genetic gain in amidst all of this climate change. So as I said, I'm really being sort of focused on this non-crossover and crossover in a statistical sense, and how do we actually think about that? And how do we use that in the models that we've got? Our prediction models, whether they're those random regressions, whether it's coming into AI, nonlinear things. But in this basic sense of it, I've got just an example with two environments, E1 and E2, some sort of a gradient going between those two. I've got two genotypes, G1 and G2. And in the first instance there, I've got this non-crossover interaction because the lines don't intersect. They're not parallel either, so they're actually diverging along that gradient. On the right-hand side, we've got this crossover interaction because quite clearly G1, the genotype 1, does better in that environmental gradient off to the right than G2, and off to the left we've got G2 is the one that is of interest. But of course, you know, these two forms, as it sort of stands, it's quite easy. You sort of look at the lines and everything makes sense. But how do we actually go from something that includes both of those forms to disentangling them and actually being able to use them? What we can think of here just quickly is that this plot on the left in the non-crossover part has got these mean yields there, whereas on the right-hand side, they're both at 0 because they're both in the intersection there. We're going to bring that back up in a little bit. So like I said, we know it's never that clear and concrete. We've got some sort of form of both of them in our midst. We've got this heterogeneity of genetic variance going on here. Can you see past me? After I've made fun of you?
I know what it is.
Okay, yeah. We've got that environmental gradient, and we've got both of those forms. We've got that non-crossing or that scaling, pulling it out, and also the crossing over. And really what the objective here is, how do we take that concept of this two-environment scenario to any number of environments so that we can disentangle it? How can we use that to then get measures of performance and stability? When it comes to stability or robustness or variability, I'd like to be able to summarize that based on the crossover interaction only rather than the non-crossover interaction. So I don't want any of that scale in my measures of stability. I'll again bring that up in a little bit. When we do this disentangling, we'd like to sort of put it in some sort of significance test. So we're not looking at the whole G by E variance, we're just looking at the parts that are causing the re-rankings, that crossing over. And like I said before, I'm not really tied to any particular model, and we'd like to be quite generalized to whether they're random regression, reduced rank regression that Hans-Peter was talking about before, factolytic, whatever those types are. So firstly, just a motivating example. This is from Don Waters' paper in 2023. He said, sorry, he couldn't make it. He was set to come, Fred. So what's going on here? Well, they're looking at barley genotypes across these different environments in Australia. We heard earlier about this Finlay-Wilkinson regression, or what started out was Yates and Cochrane. So we're looking at a regression on the mean yields of those different environments. And what we've got on the left-hand side is the scatter plot between the intercept on the x-axis and the slope. So each one of those represents the 652 genotypes there. We can see that they're correlated. So there's a correlation between the intercepts and the slope. So you're going from the left to the right of your covariate, and you're also increasing the regression slopes on that as well, with this correlation in 0.73. And the conjecture there is that if you want to then measure have some measure of performance, okay, you take that intercept. But if you're looking at robustness, stability, or whatever it is in terms of that covariate, you're doubling back up on the intercepts again. So you're going to be choosing high performing individuals, but really, how do you then take that into a selection index if you don't account for that correlation between the two? Because again, you're going to be just doubling up on those high-performing individuals rather than maybe the ones that are responsive to the covariate adjusted for the intercept. And on the right-hand side is what they've done is they've adjusted the slope for the intercept. So now they're decorrelated, they're uncorrelated. And that, negative 0.08 is just about, rounding sort of errors there. Okay, but what I wanted to do is take this example or this concept and actually use it to disentangle crossover and non-crossover interaction like I mentioned before. And that's where the statistics come in. So firstly, I'm just going to probably skip over this slide because Hans-Peter, like I said, and Fred already spoke about it, but I'm really interested in these random regression models. In this case, just an example, we've got the x-axis is just a minimum humidity, it's just a toy example. We've got the environmental covariates there. We've got the intercept there and the slope, and that's all well and good, but what I'm just going to do is put that into an equation. And so what we've got here is the intercepts for all of the different genotypes in some sort of data set. Again, I'm just keeping it quite general here at this point. They're spread out across all of the environments in your data set, so they're just repeated. They are the averages across everything, and the right-hand side here becomes the regressions on the covariate. In this example, and what I'm going to talk about next is I'm just going to shoot just one covariate, but everything's generalizable to any number of covariates that you've got in the model, whether they're the kinship model that Hans-Peter spoke about, the reduced rank, factor analytic, all of these sorts of things. Everything that follows is applicable to them. And then we've got some deviations at the end. So if you think about what the variance matrix looks like between those intercepts and slopes, we've got an intercept or a main effect variance, we've got the slope variance, and we've got a covariance between the two. Quite simple. We've also got maybe some relationship matrix on the right-hand side when we assume that separability that Fred mentioned before. And really the idea is, okay, if we go from something that is modeling a covariance between the intercept and slope, how do we rotate it in such a way that actually that covariance goes to 0? And that's what Dom did in his paper and his work, was looking at removing the covariance from the slopes and taking them away, so you get slopes that have been adjusted for those intercepts. And that's what we do here. And again, if we just do this rotation, essentially, we end up with that the new slopes here, the F stars, are independent of the intercepts. Now, Dom and co didn't do anything to the intercepts because all they were really interested in was decorrelating them in terms of the slopes, because those were the reactions on the covariates. So they were half the way there. But actually, if you do adjust your slopes for the intercepts, then you need to also adjust your intercepts for the bit that came out of the slopes. And so that's what I'm doing here. So the first part here is still the same set of intercepts as we had before, but now I'm adding in the part that had come from the slopes, and I get this new covariate for the intercepts there, or the main effects here on the right-hand side. And so if originally what we had was the intercepts repeated across all environments, we've still got that, but now in a way that they're actually different for different environments. And so we're starting to think about going from those parallel lines, what they were, to actually the fanning out. And everything now that is correlated with the intercepts have gone off to the left-hand side. And so we've got this perfect positive correlation between the original intercepts and these new ones, provided we've got a little caveat there, which I'll bring back up later on, because we don't want to bring back too much, because you'll start crossing over again. But let's say we've now got this, and so we've removed everything from the right-hand side. Now, I've just done that with one covariate and one covariance between the slopes and intercepts. But like I said before, it's generalizable to any number of covariates and any of these types of models. So what do we have? Well, now we can rewrite our original random regression in such a way that actually this first part here, which has got all the variance heterogeneity associated with the intercepts and the main effects, is actually representative of that non-crossover that I wanted from before. And on the right-hand side, we've got this, still got the regression on those slopes, on those covariates. They've not changed at all, but it's completely representative crossover G by E, the re-rankings. And so it allows me then to formally define non-crossover G by E as all of the variation arising from perfect positive correlation with those genotype main effects. And that's what I'm going to call the non-crossover. And if I do that, I can generalize it to any number of environments, any number of covariates, and so on. Then what happens is the crossover G by E is capturing all of the remaining variation that's arising from lack of correlation or re-rankings. But again, we've got this formal framework now to define it. Okay, so let's see what that looks like, I guess, back to the example from before. So this is what we had. This was if we had the normal intercepts. We've got the interactions or the deviations from them going off to the right. That's all well and good. And just by doing this rotation, I've just gone from that to this. And we've got this fanning out exclusively capturing the non-crossover G by E in the middle. And one point of difference really is that by taking that variance heterogeneity into the middle, you've reduced that lack of fit on the right-hand side in such a way that actually now we're capturing all of the main effects or the intercepts plus the variance heterogeneity, and we've got less variance on the right-hand side. So we've removed the non-crossover part from that G by E component on the right-hand side. And just to make things excellent, we've now also got two independent components. So the non-crossover and the crossover are independent, because that's what we did in the first place by decorrelating them. He's not sure if he's happy or not. I'm still thinking. One thing I will say at this point is that this is different to the traditional way of separating out heterogeneity of genetic variance and lack of correlation. And the reason why is because we're not just interested in heterogeneity of genetic variance here. We're interested in heterogeneity of genetic variance arising from perfect positive correlation with the main effects across the environments. So it's a different thing. Okay, and that's just to summarize. We've still got original covariates on the right. We've got these new covariates which have got the intercepts there. This in itself is a regression with intercepts given by the original intercepts and slopes given by the original intercepts. So that's another thing. So that's what's giving me that perfect positive correlation. But I think I'm going to crack on. You okay? I've got 5 minutes. That's good. I've got 20 slides left. Okay, so I'm going to rush through all the rest, but take it as a bonus because actually they'll be in the deck after the presentation is done, so you can go through at your own time, Fred. So, won't be reminded back. I've got 1 minute left. Okay, so why do we want to do all this sort of stuff? And I'll just show you sort of why we want to do this, right? Why do we want to separate out this non-crossover from the crossover? Firstly, I've placed the breeding objective still at the means of those across those environments. Any random regression model, I've mentioned that. We want to now look at measures of overall performance and some sort of variability and how we can go and put that into an ANOVA. I think that will wrap up what I've got here in time. So very quickly, if I was to take an average over the non-crossover part, I'm going to get back at my means, my main effects. So that's well and good. But really the difference is when I look at any responsiveness on that covariate, the F stars, I can now look at the F stars rather than the FSs. And I can also form a measure of variability. Don't worry about the equation there, it's a little bit nasty, but let's just think about it as the sum of squared deviations around the first lot of non-crossover regression. And so if I compare that to just taking a variance for each genotype, which I've done on the right, just again for that very simple example, if we don't disentangle those two components, we're going to have genotypes that are capturing more of that non-crossover in their variance, so they're going to look more unstable than what they actually are, compared to ones that truly are stable. So that's what's going on there. Again, I'll skip through this just to say that we can also take measures of variance now that we've got those two components. We've got a measure of the non-crossover variance, we've got a measure of the crossover variance, because we either look at the first regression part or the second regression part. And once we get that, we're going to have a G by E interaction variance that we can disentangle into two components as well. So we can also form, skip over that, sorry. We can also form an analysis of the crossover variance. And what I'm doing here is I'm forming up a two-way ANOVA table. I've got my genotype, I've got my environment. For this example, I'm going to assume that they're random. I've got my G by E interaction. So that top half is all pretty standard stuff. But what I'm also doing now is splitting it into two, a non-crossover component and a crossover component. They've still got the same degrees of freedom, but I'm able to actually get a variance component for those two parts. And importantly, when I want to test my genotype main effects, I no longer want to have that test against the full G by E component. I just want to test it against the crossover G by E component only. Okay. And what I'm also going to do is I can test the G by E interaction component as a whole, but I can also do the two parts there as well. And so just playing with that little example from before, I'm going to assume that my error variance is 2. I'm going to assume that I've got 2 replications. If I had time, you would have seen me show that the genetic variance was 1, because that's just the intercept variance from that example. The interaction variance is also 1, but I've disentangled it into 2 components, one part coming from the non-crossover, so all of that variance heterogeneity associated with the main effects, and the crossover. And so what I'm able to do is actually test the genotype main effect against the 2 components. So here what I'm doing is I'm testing that genotype main effects against the non-crossover G by E only, and it's coming out significant. But then if I was to do the same test with the full component, it happens to come out not significant at the 0.05 level, which is quite a nice example, and that's why I made it like that, so it looked good. But also what happens is when I test the G by E interaction component, it alone is significant, but if I look at the two components, they're not. So it sort of wraps that up quite nicely into taking those into two components. And with that, I'd like to just sum up with some conclusions. Like I said, there's plenty of slides in there for bonus for extra. So again, we've got this framework now that we can start to look at these things. Again, old concepts, a little bit new in the way of thinking about things. Applicable to many different random regression or regression models. Also applicable to, disentangling G by Y, G by L, and so on and so forth. Genotype by trait as well. So with that, thank you.
Thank you very much. Okay, one question from the audience.
Hi, very nice talk. I'm a geneticist, so this might be a very naive question, but I understand that this crossover effect then indicates that this is something genetic that you're identifying. What does this non-crossover thing mean?
Yeah, good question. I mean, one of the things I didn't touch on was once we're able to disentangle it, what you can do with it and look at what's actually driving the differences in rankings between environments. The non-crossover part is, I'm not sure, to be honest with you. I'm not a geneticist, so. But I mean, it gives you that framework to now look at the different environments that have got large proportions of non-crossover variants in them as well. And you're looking at maybe probe genotypes as well as what's doing, what's causing that scaling, to have a look a bit further in there. I mean, there's parts in there which, like I said, I didn't get a chance to talk about, but you're going to have environments that are quite well at the average environment of the TPE. I mean, Hans-Peter put up that figure. This gives you a way to actually say, what are those environments and what are their genetic variances? Are they very large? So you can go and look at them, the differences within there, and start working out what those environments are as well. So I didn't really quite answer your question, but it's a work.
Sounded quite okay. Okay, due to the time, we applaud once again.